Okay, I hope my screen is visible. Okay, can anyone confirm whether it's visible or not?
Yes, sir. Screen is visible.
Yeah, okay, thank you. Uh, so good evening everyone. I'm Sabyasachi Panda from Department of Metallurgical Materials Engineering. Welcome to this tutorial session on materials characterization. Okay. So today we are going to study a new type of characterization techniques that many people use across the world, and since we are going we have completed earlier optical microscopy, and then we have also completed scanning electron microscopy as well as X-ray diffraction technique. So today we are going to study about another characterization technique which has been well explored, and which is one of the advanced characterization technique, I would rather say, that is known as the transmission electron microscopy, or famously known as TEM. So now that we are saying that this is a electron microscopy, so what are our main motive, or what are our main goals to go to from optical microscopy, because light optical microscopy is an easier feature, and that is an easier system also for us to comprehend, for us to understand and to interpret the image of our material if we are going to image. And similarly for X-ray diffraction techniques also is an easier technique, and though it's a fundamental technique, so we are able to interpret the image quite easily. Then what is the necessity for us to go to electron microscopy? Why, if I am talking about the visible light in light optical microscopy, if I am talking about the X-ray diffraction in X-ray diffraction technique, then what was the urge for us to go to electron optics, or what was the urge for us to use the electron microscopy? So as you can see, there are different types of radiation that we can use for our imaging purpose, for our analysis purpose, or to see any different types of microstructural features. So one of the beam is visible light, which we use obviously in light optical microscope, right? So this one we use in light optical microscope, visible light. So here the disadvantage, though we can see the surface of our material, and there are different types of features also which we can analyze using the visible light. However, the long wavelength, or wavelength of this visible light is close to 400 to 700 nanometer, right? So it is quite longer wavelength when we are talking in terms of electromagnetic radiation, because electromagnetic radiation, after visible light there will be ultraviolet light and UV rays, and after UV rays there are X-rays, and after X-ray there are gamma rays. So if we are talking in terms of those electromagnetic radiation, the whole spectrum of electromagnetic radiation, then the visible light offers us long wavelength. And what the long wavelength has to do with our system or optical system, what it does, it limits the capacity of microscope. When I am telling the limits the capacity of the microscope, that means I am talking in terms of resolution. That means it limits our resolution, so that we will not be able to use exclusively to see a very small features which are in the order of nanometer, small features which are in the order of micrometer. So though this is a type of electromagnetic radiation, then due to this due to this long wavelength disadvantage, we have gone to an other type of radiation. What are the other type of radiation I talked about? One of them is X-ray, and X-ray we know that it is a high energetic electromagnetic radiation with the wavelength of 10 to the power minus 9 meter to 10 to the power minus 11 meter. Okay, though X-ray is an extremely good for us to analyze our samples, to identify the phases that are present in our sample, to analyze the texture in our sample. Though it is an extremely useful tool for us, but the problem with X-rays, it is very hard to focus through glass plates. Why it is very hard to focus through glass plate, or you can say any thick sample, if you are going to put or if you are going to get any any kind of information. Why? Because of the absorption coefficient and the absorption nature of the X-ray. Why? Because when specimen, let's say this is a sample, and when X-ray comes, let's say this is X-ray, incident X-ray, then there are large portion of this X-ray are getting absorbed by the sample, and very small portion will be either transmitted or scattered. Okay, so due to this phenomenon, due to this disadvantage of the X-ray, so we cannot obtain the complete information, or it is the due to this absorptivity nature of this X-ray, we are not able to analyze our material as much as we want. Then there is another type of radiation which is actually neutron radiation. We all must have heard some at some point of our time neutron radiation. There are different types of reactors around the world and which produce the neutron radiation, and using neutron radiation we also do our diffraction experiments, and finally we get the results. Okay, it is also another powerful tool. However, powerful tool to analyze our samples. However, the advantage is it is having very small wavelength, which is one of the greatest advantages of neutron. And with this neutron there will be low sample damage. Always we also have to take care of our sample damage. Why? Because if we are putting our sample in terms of any electromagnetic radiation which is carrying very high amount of energy, then the sample damage will be there, and the information that we will get from this kind of analysis will be wrong, because it will be carrying information from not only our sample but also from other sources like contamination from the sample damages. All these phenomena factors also we have to consider. But the disadvantage of this neutron is, though it is an excellent, it offers us a very small wavelength and low sample damages, the disadvantage is associated with neutron is how to produce them, because it is not very easy for us to produce a neutron beam, and that neutron beam has to continuously it has to be produced, so that we will get a proper proper diffraction pattern or proper image. So and another thing is how to focus the X-rays, how to focus the neutron. So these are the two major disadvantages in front of us, for which we are not able to use neutrons as our go-to radiation for which we want to analyze our sample. So due to this reason, what we do, we go to another type of radiation, that is the electron radiation. Okay, so why we are going to electron radiation, why the radiation that we are using, that radiation is that radiation consists of electron beam. That means number of electrons if we are able to extract, then we use that electron to image our sample. We use that electron to get a diffraction analysis. We use that electron to also do different types of chemical analysis, spectroscopy study. All these things also we can do. So what is the advantage if I am telling that this electron we are using now instead of visible light, X-ray and neutron? It's not that we are not using neutrons, not using X-rays, but the disadvantages that are associated with this kind of radiation, we have switched to electron. So if we are using electron, then what are the advantages of electron? One of the advantage is it is having wave-like property. Okay, so electron can be considered as a particle, also electron can be considered as a wave, and it also offers same advantage as the neutron. That means it is also having small wavelength, and small wavelength is good for us. Why? Because we will be in that case getting a better resolution. Once we get the better resolution, the very nanometric features also we can resolve the distance between, as we will see in the subsequent slides, that we will using an electron beam, we will be able to resolve the distance between two atoms. Okay, so that much resolution we will be able to get using this TM instrument. And that means the small wavelength, what is the amount of that small, what is the exact number if I am talking about in small wavelength, then we can say that this is in picometer. Okay, I will write it here. The wavelength of electron is in the order of picometer. So picometer means 10 to the power minus 12 meter wavelength. Okay, and when I am talking about two atoms, the distance between two atoms, okay, when we are talking about the distance between two atoms, that distance is in the order of angstrom. That means 10 to the power minus 10 meter. Now okay, so now if you remember in the first class of materials characterization, I have told three criteria for diffraction, reflection and transmission. So the what is the criteria for this transmission? So the criteria was, let's say one wave is coming, okay, the wavelength is lambda and the distance between these two objects is d. And in this case, if I am talking about, if lambda is very small than d, then transmission happens. If lambda is equivalent to d, then in that case what will happen? That case diffraction will happen. If lambda will, okay, I am writing it here, if lambda is equivalent to d, then diffraction will take place. If lambda is very greater than d, then in that case reflection takes place. Okay, these are the three conditions that we have seen throughout our courses, that when the wavelength of the incident beam will be equivalent to, less than or greater than the distance between the two scattering objects, then what are the phenomena that will take place. So in this case, since we are seeing that the wavelength here is 10 to the power minus 12 and wavelength wavelength of the electron, and the distance between two atoms or here two scattering objects or two atoms is in the order of angstrom, that means if we want to use electron to view our atoms in our material system, then we will be able to see them. And also how we will be able to see them? By the process called transmission. So that is why this electron microscopy which we are going to use now, that microscopy is known as transmission electron microscopy. Okay, and now yes, so this microscopy we are going to use, and this is known as transmission electron microscopy. So there are different companies which make this transmission electron microscopy, though it is not a smaller task to make a transmission electron microscopy, but it is easier as compared to the neutron radiation. So that is why in many of the laboratories we are seeing this the frequent use, more and more use of transmission electron microscopy to view the features and to resolve the distance between atoms. Why? Because as for Moore's law, if we are talking about, then the number of component that we are number of component, I mean the number of transistor, let's say number of transistor in a certain amount of area if we are talking about, then it is decreasing year by year. So that means more and more number of materials are going inside this inside a chip, I would say, then either to see what are the features, to see how they are behaving, and to see how they are behaving under what is their performance, how they are performing under specific condition. So we need to resolve the distance between the atoms of those materials. And when we are talking about resolving the distance between atoms, that's why we are using this transmission electron microscopy. And as you can see, these are not any small equipment as compared to ACM and as compared to optical microscope. How they are big component. Here one person is sitting, these are the two examples I have taken from this textbook, Barry Cutter. So here you can see one person is sitting, and the transmission electron microscope size you can see it here. So these are really big instrument, and this is an instrument, and also with in addition to this instrument, there will be lots of electronics associated with this. Yeah, from these this is also another TEM instrument. So here we can see that this is an if I would so this is a phosphorus screen. If you can see, this is a phosphorus screen where we view our sample, and these are the electronics associated with them. And so this is a typical example of transmission electron microscopy. So from here to here we are also advancing in the field of transmission electron microscopy. Yes, and this is an advanced variant of microscopy technique, and we use the diffraction physics and electron optical system. We how the diffraction takes place in a material, how the diffraction takes place in a from a specimen. We use those physics, and then finally we implement the electron optical system. We use several kinds of lenses. We use different types of the stigmators. We use different types of deflector also, and aperture also. The combination of all these things will be stayed inside this chamber, and this chamber is known as the electron column, and this whole entire system is we keep it inside a vacuum, because electrons are prone to scattering. As we have seen, the electrons are prone to scattering, so we maintain a high vacuum also, and using all these techniques we finally image our material. Okay, and yes, I mentioned in the previous slides that X-rays are prone to absorption in when we are putting a glass in front of them, and electrons also, they are also prone to absorption. The penetration power, the penetration depth, if I am talking about the penetration depth of electron, it is close to 100 nanometer, right? So if we are seeing, so transmission means, let's say I am preparing a sample, my electron beam is coming, and then after the interaction with the sample, what kind of beams I am getting. So far what we have done in scanning electron microscopy, in transmission electron microscopy, we are putting our detector so that we will be observing this kind of either backscattered or secondary electron, or Auger spectroscopy if you want to do, or fluorescence spectroscopy. We are always observing backside electrons. Now in transmission electron microscopy, we will be taking this side. So these are the transmitted beam. So these are the transmitted beam. One of the transmitted beam might be direct beam, another of the transmitted beam might be elastically scattered beam, another one will be inelastically scattered beam. So now we are going to put our detector after the electron passes through the specimen. If this is our specimen, okay, if this is our specimen, after the electron beam interacts with our specimen, what kind of information it is carrying. So now here we will put our detector. So as you can see, if this is my electron gun here, okay, so if this is my electron gun and it is coming all the way here, let's say, and this is my sample chamber. If my sample chamber will be somewhere here, sample chamber, this is the screen where I am seeing, my detector will be somewhere in the downside. Okay, and not only my detector will be there, and also along with my detector some energy filters will be there, which enables me to do different types of spectroscopic analysis. We'll see what are those spectroscopic analysis in further classes, but this is how a transmission electron microscopy is generally operated. Okay, so now coming to means interpretation of TEM images. If we are going, let's say we have talked about the TEM machine as a whole. We have not gone into the details of that machine, which we'll do. But now let's say what is the output of a TEM machine. So if I put my sample, let's say I create a sample of less than 100 nanometer, and I put the sample in the sample specimen chamber, and finally I get some output. So what is the output of this thing? I will get two different types of output. One will be image might be dark field image might be bright field image. How we will get those things, we will see the fundamentals behind those things. But one, I will get image, and also another thing I will get as diffraction pattern. Okay, these things are called as DP. Diffraction pattern is DP. Okay, so these are the different types of information that I will get from a TEM machine. Okay, and as mentioned here, you can see this is an image. This is an TEM image of the material is, I think, strontium titanate. Okay, this is a material, so these are the strontium titanate material. Here you can see there is a twin boundary associated with it, and all the dots that you are seeing, the dots are nothing but the atomic column. Why I am saying atomic column? Because the information or the image that we are getting from a TM sample, I am saying that TM sample or the specimen will always be an average through the thickness of the specimen. What do I mean by the thickness? I will tell you in the next slide. But information is always average through the thickness of the specimen, so it is never, so all the dots you are seeing, if you are so if the distance you can see here, it is written as 1 nanometer. That means we are going to see the sub nanometric features also in the specimen. And here if you can see, this one is a twin boundary. Twin boundary means what? And this one also is a twin boundary. If you look close enough, then you can see towards this side of the, towards the top side of this boundary, the plane, the atoms are situated in this manner. I am drawing, and towards the bottom side of this horizontal boundary, the atoms are like this. So that means here this is a, in between them is a clear twin boundary. So these are the different types of features which we were not able to see in scanning electron microscope, or also we are not able to see in light optical microscope. That is why we are using TM images. So this is one type of image that we are getting in our from our TM instrument. And here also you can see the same image, these two, let's say this is image 1, this is image 2. So same image also, after doing some after using the filter, different types of energy filter, after you see the, now in the second image is quite comprehend, it is quite comprehensive, while the first image, this image is a little bit blurry. Here the contrast mechanism, by the use of energy filter, we are clearly able to see where the atoms or the atomic columns are situated. And similarly, if you come here, this image, if you see, this image is called as diffraction pattern. And the diffraction pattern, in the diffraction pattern, if you are seeing, this material is gallium arsenide. Okay, the example has been given in this book. I've taken it from this textbook. You can go through it. So this is a diffraction pattern. So what do you mean by diffraction pattern? Diffraction pattern is nothing but a collection of all the planes in the reciprocal space. When I say that collection of all the planes in the reciprocal space, then when we are talking about the reciprocal space, we have defined the reciprocal space in such a way that in reciprocal space the real planes will be always points, right? In points in reciprocal space will be three-dimensional real planes. That's what we have known, right? So three-dimensional real planes will be points in reciprocal space. So these points, if I am talking about that, this diffraction pattern is a collection of all the points in reciprocal space, or the collection of all the planes in reciprocal space. That means whenever I am talking about this point, this point, this point, this point, they all represent to the real space planes. Okay, so the collection of all these points, I call it as diffraction pattern. Okay, there may be, and these diffraction pattern will be will only come when the diffraction condition gets fulfilled, and when the diffraction condition gets fulfilled, when the Bragg's criteria, also the Bragg's law, is satisfied. And how the diffraction condition gets fulfilled, how the Bragg's law gets satisfied, if you come to the original term, what was the condition? The condition was the reciprocal points in reciprocal space must come onto the surface of a sphere. That sphere is known as a world sphere, right? So when the reciprocal lattice points come unto the surface of evolved sphere, the criteria of diffraction gets satisfied, and when the criteria of diffraction gets satisfied, you get these kind of points, and due to that, since these points come due to the diffraction, so that is why the pattern is known as, pattern is known as diffraction pattern. And you will notice in further classes that this diffraction pattern is subjective to crystal symmetry, it's subjective to the interplanar spacing of a particular material. Okay, so due to that, due to this kind of relationship between the diffraction pattern and the symmetry and the interplanar spacing, you will get lots of information by simply indexing this diffraction pattern. Remember, we have done our indexing in X-ray diffraction, but here there is different types of indexing which is associated with this diffraction pattern. Okay, and now so here also there is these two images that I am talking about. These two images also, it is an information average through the thickness, and here you can see that this might be some of the, and here the second point I want to highlight is no depth sensitivity we will get. That means whether the electron has whether the electron has collected information till a certain depth or not, we do not know, because the electron is transmitting through the specimen, and whatever the information it is getting, it is we are assuming that the information will be completely completely from the material. However, in this case, when we are seeing some of these dots kind of structure, we may assume that these features belong to the material, right? That is what we may assume, but we cannot say for sure that until and unless we do other characterization technique, we use other characterization technique in TM, we cannot be certain, we cannot be fully certain that these are the features of a material. Why? Because these might be different types of damage. We talked about the beam damage, right? Electrons are, when they are coming they are highly energetic beam, and when highly energetic beam come and interacts with your material, there is a high chance of electron the beam damage also. So this, whether this is a pit kind of structure or it belongs to your material, or it is a second phase in your material in a matrix, then we are not sure. So that is why this TM image, interpretation of a TM image is not as simple as the interpretation of other microscopic techniques or other optical techniques. So that is why no depth sensitivity is there. And why I say that this information is average throughout this information is average throughout the thickness of our material. Let's say I'm taking a material here, then let's say this is a material if I'm talking about. Okay, this is my material, and the electron beams are coming like this. Right? So if I'm talking the electron beams are coming like this, then why I am saying okay, here these are the transmitted beam going in all direction. That means the average, what do I mean by the average is that if my atom, if my total material, let's say like this, if I break my total material into different atoms, let's say this is the thickness is somewhat some nanometer level, and if I am breaking this thing and saying that these boxes, for now let's consider that these boxes are, one box belongs to one atom. So when my electron beam comes, and then I will get information from all this thing. That means my electron beam will interact with all the specimen, all the atoms, and in some cases if I have to let's say I am taking the energy of, I am considering in some cases I will be considering what will be the, let's say this is the incident beam energy, what will be the transmitted beam energy. Let's say I am considering now the transmitted beam energy. So if I am considering a transmitted beam energy, let's say in this direction I want to plot the energy. So energy will be in this direction, right? Let's say this is I'm talking about x, and this is I'm talking about y. If this is the direction, then here let's say just the incident beam electron touches the sample, so here the energy amount will be extremely high, let's say. And once it interacts with these different types of atoms, which different types of atom means there's different types of boxes, once it's interact, then its electron energy will be subsequently going down or like this. Okay, so this is why, so this is an example of energy I have given. Similarly, if there are instead of, now I have taken all perfect atoms, let's say there will be dislocations associated with somewhere, then according to the dislocation, according to the defect, according to the extra material that are present somewhere inside my inside this atomic column or the atomic row of my material, then the electron beam will also get diffracted, get transmitted, get elastically scattered and inelastically scattered. And when those things will be happening, I will, in my image, what I will get, I will not get a I will not get let's say this is my material. In this case I might get some dark mechanism, some dark contrast I will get in this case. Okay, and in around this dark contrast I will get this bright let's say bright region I will get. Okay, only in this one I will, in a certain thing I will get a dark region. So in this case I will not be able to comprehend at what depth of my material this defect or let's this extra dislocation is lying. However, I know that among from somewhere this total thickness, if I am talking about, if I am considering the total thickness, uh, among this total thickness somewhere there is a dislocation, but at what depth the dislocation is, whether it is at the surface, whether it is just the exit of this electron beam, I will not be able to comprehend. So that is why this depth sensitivity, when I am talking about the depth sensitivity, means we cannot know for sure that the penetration where the particular feature of this particular feature of our sample we are getting it from, and that is why the information that we are getting, it is always averaged. And here you have seen just an additional information I want to give it to you. You have seen I have drawn a different set of atoms. So now one atom will be one atomic column, another atom will be atomic row. So what I have drawn now, that I have told that the incident beam, if it is getting information by interacting with all these atoms, then I will get a TEM information. That means transmission electron, and this is called as conventional TM. Conventional TM image or conventional TM diffraction I will get. However, if I will draw, okay, if I only want to see or get the information from one atomic column, okay, so if I want to get the information from one atomic column, let's say this is one atomic column. If I want to get the information from only one atomic column, then if I am talking about one column, then that technology, that information I use STEM, that means scanning transmission electron microscopy. Why I call it scan? Because I want to gather information first from one atomic column, that, and then when I gather the information from one atomic column, I go to next atomic column. Then when I gather information, let's say this is 1, this is 2, this is 3, this is 4, this is 5, this is 6, right? So when I gather information from one atomic column to another and then I go to second atomic column, what do? I scan the electron beam here, scan the electron beam. And once I scan the electron beam, that is why this technique is known as STM. This is an advanced technique of TM itself. TM is already an advanced technique. However, STM also is another advanced technique of this TM. Why? Because I am collecting information, then I am going to I am going to scan the my atom. So that is what this is known as scanning transmission electron microscopy, STM. Similarly, I considered one column. Now if I consider, here I am writing, if I consider one row of atoms, that means I want to gather information from one particular, at a particular height, or I want to gather information about one row of atoms. So that row of atoms, how I will gather the information, that I will use that spectroscopy technique that is called as yields. That means in this row, if I am talking about this entire row, then what are the variation in the energy level that I want to see, I will finally get when I put my detector. So that spectroscopic technique is known as yields. Yields is nothing, the full form of the yields is electron energy loss spectroscopy. Okay, so it is a spectroscopic technique that we use in transmission electron microscopy. So these are the two additional information that we have to consider. Okay, now yes, so now what is the point that we should use this electron transmission electron microscopy. So there are different, what are the kind of information that we might get from TM. We will get crystal structure, we will get point group, we will be able to get space group, crystallographic symmetry, and then lattice parameter. All this information that I am talking about. So dislocation arrays, grain boundaries, chemical analysis. Grain boundaries we will be able to also see it in scanning electron microscopy. But however, if you want to visualize that, if you want to see what are the atomic position inside the grain boundary, then we have to go to transmission electron microscopy, right? So this is an example of a transmission electron micrograph, where we can see so here this is also an extremely good example of depth insensitivity of transmission electron micrograph. Here we cannot say that this top portion where I am writing it now T, this is top portion and this is bottom portion, let's say. We cannot say that in the material itself that this is the top portion and this is the bottom portion. Okay, we because it is appearing from this micrograph, it is appearing that this is top portion, and whatever this thing is there, it is a step kind of structure, and below this thing it is a bottom portion. Okay, though it is appearing as a steps kind of feature, but in reality it is not the case. So that is why. And what are these things? These lines are coming, these lines are the dislocation bands or the dislocation arrays which we talk about. Dislocation is a one-dimensional defect. Okay, dislocation is a one-dimensional defect where this happens when say a series of atoms are not positioned in their actual lattice position, and are not placed, the series of atoms are not placed in their actual lattice position. So that is how the dislocation form. So there are different types of dislocation which we also see it using this transmission electron microscopy microscope. And here crystal structure, that means when I am talking about crystal structure, this is FCC, whether it is BCC, whether it is monoclinic, whether it is orthorhombic, hexagonal, or simple cubic. So these are the different types of information we are able to get. When I am talking about point groups, what do you mean by point groups? So the point groups is that what do the point group describe? So they describe the symmetry operations. Okay, so the number of symmetry operation that can be performed on a crystal around a point without changing its appearance. Okay, so that is what known as the point group. And how many point groups are there? There are total 32 point groups are there, right? And if I am talking about space group, then space group describe nothing but the symmetry of a crystal lattice, which includes symmetry like translational symmetry. That means the repeating patterns if I do to a crystal lattice, then whether I will be able to get the able to get the Bravais lattice, because we know that in materials system there are 14 Bravais lattice are there. Okay, so whether I will be able to do I will be able to get this 14 Bravais lattice or not. So That is my ultimate motto. So how many space groups are there in a material system? That is 230 space groups are there. Okay, so the combination of these point groups and space groups, so these point groups symmetry operation means rotation and reflection we are talking about, and the space group symmetry if I am talking about, then this is translational symmetry, those kind of symmetry I am talking about, and the combination of point groups and space group we are trying to always get this 14 number of Bravais lattice. Okay, so these are different types of information that we are able to extract from transmission electron microscopy, right? Now let's go to we know why we are using the transmission electron microscopy. We have seen how the transmission electron microscopy is used and what are the outputs of this transmission electron microscopy. Now let's go to the to a little bit detail into this transmission electron the TEM. So so electron microscope means, if I am talking about the electron microscope, then definitely I need a source, and that source is given by an electron gun. Okay, so this is an electron source. So if I am talking that this electron I have to generate electron, then just whether I have photos, no. Okay, if I have to generate electron, then I have to use some kind of electron gun, and the electron gun, there are different types of electron gun which we have already read and still we are going to read in the next slide. So we need electron gun because that is our source. Then after gun we use these electromagnetic lenses. Why we use electromagnetic lenses, optical lens, glass lenses? Because of the penetration power of the of our electrons, right? And then comes the column and knobs. So this is the column, this column, inside this column the vacuum is maintained. So basically if I am talking about the column, this column contains all these things also: electron gun, electromagnetic lens, sample chamber where the sample is inserted, though there is a specific sample holder will be there. Okay, we cannot use our we use any type of any material here in the transmission electron microscope. The materials dimensions are a constant, so we cannot use any random shape, any random size material. So for that since it is a constant in the electron microscopy, so we need a particular or a specific sample holder. And then comes energy filters, which I talked about, the electron energy loss spectroscopy. So those kind of energy for to detect the energy loss, we need some energy filters also. So like band pass filter and different these kind of filters we will study. And then finally the detector. This detector is also one of the important system, because after the interaction the electrons will be collected somewhere, and finally it will be imaged through different different system, and that is detector system. Ultimately, when we are talking about the electrons as our incident beam, we need vacuum system. Why? Because otherwise if we don't provide a vacuum system, electrons will be scattered through the air. Why? Because in air also gas molecules are present, like oxygen, like nitrogen, like different particles are also there, so they will scatter our electrons. So this vacuum that we do for a conventional transmission electron microscope is in the order of 10 to the power minus 5. This is the vacuum system. Remember, atmospheric vacuum is, if I am talking about atmospheric pressure, this is 10 to the power 5 Pascal, right? So it is, you can say, almost more than a billionth time. So more than a billionth time vacuum we have to maintain. 10 to the power minus 5 Pascal we have to maintain. However, the our atmospheric pressure is 10 to the power 5 Pascal. So this is the basic basic components, or these are the basic systems, I would rather say, not components, because inside this each of these systems there are different types of components present. So these are the different the major systems of a transmission electron microscope. Now coming to the electron sources. So electron sources, as we have seen, there are different types of electron gun which provides the electrons from those materials. And what was the fundamental, what was the phenomena behind that? If anyone can say, the temperature is when the material is heated beyond 2700 Kelvin. Okay, then what will happen? This tungsten wire or material, they emits lights as well as electrons, and our focus is to only collect this electron, right? So when we are providing so the electrons will be coming out, and when we are going to provide the huge accelerating voltage to those electrons will be going at a very high speed towards our sample. Okay, and electron sources are two types. One is thermionic gun, another one is field emission gun. Okay, so why we have chosen thermionic gun and different types of field emission gun also. So thermionic gun, because this is a tungsten, we are talking about the melting point of tungsten is greater than 3000, and so that is why, since not every metal can be used as a electron gun, and this is a lanthanum hexaboride or called as lab 6 material. So this is also another thermionic gun. So thermionic gun means we are only providing the temperature greater than 2700 Kelvin, right? So this is a thermionic gun, and the also we are providing field emission gun also acts as an electron source. How this thing, they are the three different type: cold, Schottky and thermal. And why we are using these different types of electron sources? Because one of the major criteria we have noticed is that the brightness, we will obviously get brightness, and brightness is, if you remember, so the brightness is, so it is defined as beam current density per unit solid angle. Okay, and how do we define the solid angle? What is the unit of solid angle? Solid angle is defined, the unit of solid angle is sterradian, right? And the brightness unit, if I am talking about, then ampere per meter square per sterradian. Okay, so this is the unit of this brightness. So as we go from thermionic gun, that means from tungsten wire, to lab 6 to cold and Schottky and thermal field emission gun, then our brightness will definitely increase, and this is one of the major reason that we use the field emission gun. And what is the order of brightness that I am talking about? If I am using a tungsten, then it will be 10 to the power 8 ampere per meter square this per steradian. If I am talking about lab 6, then it is in the order of 10 to the power 9. And when I am going to field emission, so what do I mean by field emission? I, instead of using this temperature, what I do, I use the electric voltage. That means I provide I make a very fine tip, like here. If I am making a very fine tip, then if I provide a huge amount of positive potential, then the electron will start coming out from this tip. Okay, and this is a process called tunneling, and due to that process the electrons will start coming out. And if that value, that electric that voltage that I am providing is producing an electric field greater than 10 to the power 9 volt per meter, then only the electrons will come. Not like if I produce it, if I give a 10 volt here and then I keep a 1 meter tip or 1 meter radius tip, then the electron will start coming. No, the electric field has to be 10 greater than 10 to the power 9 volt per meter. So when this phenomenon, when I am applying this high amount of electric field, then the electrons will start coming out, and finally I will be getting electron beam. Okay, and also another reason from that I see from thermionic gun, that is called coherence. So coherence means there are two different types of coherence is there. Okay, so here I'll just tell what are the difference. So here you can see one tungsten wire is there, and here this tungsten wire is bent like a pin. And though this is an extremely exaggerated picture here, but this the radius of this pin is in the order of nanometers or in the order of micrometers. Okay, so that will be the radius of the pin. Same, this is a lab 6 material, and this is a cold FEG. cold field emission gun, where the field will be produced and the electrons will be coming out like this. And if you can see here, this is an image is an under saturated cold field emission gun, and this is a saturated means the electrons are coming at a maximum with the maximum brightness. Okay, so I talked about a term called coherence. So coherence means whether all the electrons which are coming, they are focused at single point or they are focused at different point. Why? Because that is necessary for me if I want to view my sample. So there are two different types of coherence are there. I am writing it here. One is spatial coherence, another one is temporal coherence. Okay, so spatial coherence means all the electrons should be coming in the same direction. If they are not coming in the same direction, then what will happen? Let's say my material is like this, okay, and one electron one electron will be focused here, another electron will be focused here. Then in that case, if my sample is, if there is no spatial coherence between the electrons that are getting produced from the electron gun, then I will not be able to view the sample properly. What will be the problem in that case? My image will be blurred, because all the electron beams, they will not be focused at a single point. They will be focused at different point and giving to also before interaction as well as after interaction with the specimen. So they will give me blurred image. What is the temporal coherence? Temporal coherence means same speed, whether all the electrons are coming at the same speed or not. Let's say my lens is there. This is one of my lens I am talking about. One electron will be focused here, one electron will be focused here. Okay, if this kind of electrons, if I am talking about, this is one of my projector lens and one electron will be focused here, that means my first image will be formed here and my second image will be formed here, right? So in this case also, since all the images are not getting formed at a single plane, then here also I would get a blurred structure. And due to this phenomena, so this is the spatial coherence and temporal coherence. So this tungsten tip which we are talking about, so it is a tungsten tip. It is not very coherent. If we are considering the spatial and temporal coherent, this tungsten tip is not very coherent, and this lab 6 nearly coherent. Okay, nearly coherent, and it is also having very sharp tip. Okay, and this fag which we are talking about, they are coherent. And this coherency, you can see the energy spread. If you see this row, energy spread, here you can see 0.3 electron volt energy spread is there. However, here 3 electron volt, 1.5 electron volt. So this fag which I am talking about, they are coherent, and they also have a very sharp tip. Okay, and this cold fag which I am talking about, entirely we dependent on this electric field. That means the whole amount of electron will be coming from electric field. And this thermal fag which you remember here, this thermal fag, so this thermal fag, first we heat the filament to a certain value, then we apply the electric field. Okay, and these are different. So this table we have seen it earlier in our first electron optics class. So here we can see the work function, and another feature is also brightness. Brightness is also one of the important feature for us to select the electron gun. Okay, and also this lifetime. So this lifetime also you can see in the fag, the lifetime is for more than 5,000 hours, which also reduces the which also increases the service time. Okay, and coming to this electron gun, so how the electron guns are getting extracted. So here this is an electron gun consisting of this this consists of a lab 6 crystal, and here you can see once the electrons are pulled out. So once the electron gun the electrons are pulled out from the electron gun from this material, whether by heating or by applying electric field, then they will be having tendency to go in all directions. Once they will be having once they are having tendency to go in all directions, then we cannot focus them into a single point, and if we are not able to focus them into a single point, then we will be getting blurred images. So that is why there is a cap called Wenelt cap. So this is an example of Wenelt cap. Okay, so what is this Wenelt cap? So it is a electrostatic lens, nothing but a electrostatic lens. And this electrostatic lens, how do we provide this electrostatic lens? So we provide a little bit of negative charge to this electrostatic lens, and so since this is having little bit of negative charge, and electrons are also negatively charged, so they will be focused like in this diagram. If you see in this diagram, in this section, so electrons are first, they are diverging, then slowly they are converging to this point. So this is where they are converged for the first time. That point is called as gun crossover. Okay, and the gun crossover depends how fine our beam will be. We want as minimum d naught value as possible. And why the electrons will be coming to downside? Because we have provided a anode plate. What do you mean by anode plate? Anode plate is nothing but a positively charged plate. Since electrons are negatively charged, we are providing extremely high positive charges to here, and finally we are able to extract the electron, and the electrons will be accelerated towards the specimen, and after this they go to the anode plate. Here the specimen will be there. And what will happen if we are not going to provide we are not providing the Wenelt cap? What will happen? And so here there are three scenarios which we have taken. In the first scenario, you can see that if we are not providing any bias, that means no bias, that means no divergence, no negative charge we are giving to Wenelt cap, then some of the electrons will hit anode here at this point, though we are getting maximum current, but we are not getting we will not be getting a point source in that case. So this gun crossover, it actually defines our source. Okay, because from this point onwards, all the electrons are going to be used to interact with our sample and further to get the information. So if we are not using any kind of bias in the first case, so the electrons will be diverged, and some of the electrons will be lost in the way. If we are applying high bias, like in the case of third, if we are applying high bias, then here this is negative charge we are providing. Let's say Wenelt grid, we are highly negative charge we are providing, then there is a chance that the electrons will go back without heating. That means we are not going to get any kind of current here. Okay, no current we will be getting. So this is why the Wenelt cap, in the Wenelt cap, the optimum bias is always required, which will give us intermediate current. But however, we will be able to get a focused gun crossover. So this is what is important for us, the gun crossover. Remember, this d naught is important because we like the demagnification term or the magnification term, or in further the amount of the resolution, the size of the probe, all these things are determined by this d naught. That means the diameter size of this first gun crossover. So that is why this electron gun is important. And if you want to say let's say how we are providing this thing, then the schematics I'll just draw it. So let's say this is my electron. Okay, so how we are going to provide this thing? Let's say electrons are coming out. Okay, and the electrons, when they are coming out, and this is my Wenelt cap. Okay, so the Wenelt cap is, so this is used to focus the electron that I am having current, right? And so when I apply some sort of electric field, the electrons are coming out. So how do I how do I make them come towards this thing? So what I will do, I talked about the possibility of the, I talked about installing the anode, right? So but how I will ensure that this anode will be extremely positive potential? Let's say I am applying voltage of minus 300 kV, right? So this is a negative voltage. If I am talking about minus 300 kilovolt, if I am applying, then electrons, so since this is a van Heldt gap, my all the electrons will be focused here, right? So this is my, let's say, D naught. Then what I will do, I will be, so this is a van Heldt gap. What I will do, I will have a series of connection here, okay, throughout my column. I will have a series of connection, so that in such a way that there will be a flat electric field, okay. So there will be a flat electric circuit I will be having in such a manner that this final one, okay, this final one I will do grounded. So this entire segment that I will do, I will have, there is an electric circuit where the electric field will be there. And if I am talking about that at the starting I am having minus 300 kilovolt, if at the end of my microscope column I will have circuit in such a way that here, since it is grounded, it will be having 0 volt. That means the effective electric field I am applying here, what will be the effective electric field I am applying? This is 0 volt minus this is minus 300 kV. That means the effective electric field I am applying is 300 kilovolt. So this is what I mean by the anode, plate which is extracting the electron. So since this is in negative and this is 0 volt, that means this for this electron there is an anode plate here, and they will start coming in a particular directions, okay. Since they will, and how I will do, I will make sure that they will follow all this direction. Let's say this is kept at minus 300 kV. I will keep this van Heldt gap as minus 300 kV minus delta. Delta means some value I will keep, okay. Let's say for now delta is somewhat 30 kV, 0 to 30 kV. I'll keep somewhat this thing. Then what will be the here, let's say in this position, what I will do, in this position the voltage I will give as minus 270 kV. At this point my voltage will be minus 240 kV. At this point my voltage will be minus 180 kV. Similarly, when I am coming to this point, my voltage will be minus 30 kV. That means, and each and every point of this beam of this column, if I am talking about this is my column, at each and every point of my column the electrons are experiencing some sort of accelerating potential to go to downside. So that is how I control the beam of electron to go and let's say hit my specimen, or go and interact with my specimen. After that I will get the information that I need. And this is the reason why it is extremely important. Remember, I am talking about minus 300 kilovolt, and this is why, if that means my entire electron transmission electron microscope has to be grounded, and it has to be grounded well. So this is why many situations, many cases you might have heard that for electron microscope, for the transmission electron microscope, the ground, the earthing or the ground work is solidly needed. If the earthing that we are providing for the transmission electron microscope is not good enough, then there will be charging effect which takes place. So at some point of time we all must have heard, we may have heard that the ground there are some issue with the earthing. So that is why the electron microscope is not, we are not able to open the electron microscope. So this is the case. Why? Because this microscope is entirely connected in a circuit where the ground, the last one is it is grounded. Now the problem is, if it is not properly grounded, or it is not 0 volt, it is having some amount of volt, then the electron beam path will be deviated. So that is what we don't want. So that is why all the electron microscope, if you observe it closely, all the electron microscope are kept in ground floor of any of the building, so that they will have a proper proper earthing. Okay. And yeah, now coming to the column, if I am talking about the what is the I talked about the basic system of the electron microscope. But if I am talking about the column contains the all the things. Let's say this is, I'm talking about, this is a filament. Okay, and then this one is Wenelt cylinder or Wenelt cap. Okay, so this is what gun. Then there comes the acceleration stacks. If I am talking about acceleration stacks, right, so this will give some acceleration potential to the upcoming electrons, right? And then comes the, after gun acceleration stack, then comes the condenser lens system. Okay, so what will be there in condenser lens system? So remember, when I am talking about any of the lens system, it will not only be the lens. So with lens there will be three other components which are associated with that. One will be deflector. What is the role of deflector? So if my electron is going away from my intended path, away from the intended path to so that it will not be focused, the role of deflector is to stop that. After deflector there will be always lens, and after lens there will be stigmator. So what is the role of stigmator? The role of stigmator is to minimize the astigmatism as much as possible. And finally there will be aperture. So when I am talking about any of the lens system, this lens system will be having these four components: deflector, lens, stigmator and aperture. So this is the condenser system. Okay, so here these things will be there. Okay, and this is I'm drawing this kind of lens, but ideally there will be pole pieces will be there, so this lenses will not be there. And then finally, if I am talking, let's say I am drawing a column here. Okay, so if so, this is my condenser lens system. Similar case also will be, this is my sample, and my sample so this is my specimen, and this is my holder, specimen holder. And so here this will be a in this point there will be a crossover point. That means the gun crossover which I was talking about. And this is the condenser lens system. This will be my objective lens system. So when I am talking about my objective lens system, that means I am having these four components in that lens system. So after the interaction with this thing, then there will be series. So what is the purpose of this condenser lens system? If I am talking about, the purpose of the condenser lens system is to focus the electron beam onto the sample as much as possible. That is the purpose of condenser lens system. If I am talking about the objective lens system, then so here I will give the deflector, lens, and then aperture and all the other things. So when I am talking in terms of that thing, then the this thing is, it is the produces, so the purpose of this thing is produces the magnified image, produces the magnified image of the sample, right? So this is what called as, okay. And after this much, then after the objective lens system, then finally it will be, there is another system will be associated with it, which is known as the projector lens. So the job of this projector lens is to further magnification. So we do not stop at objective lens, we have also another series of lenses, so that is further magnification. Okay, that is projector lens system. And this projector, in the projector lens system we are having different types of projector lens system. That is intermediate lenses will be there, intermediate lens 1, intermediate lens 2, and similarly projector lens 1, projector lens 2. So their job is to further magnify. So if I have to tell that let's say what is the job of means how we are achieving the final magnification that I am talking about currently, then if so the magnification happens at what point? The magnification happens beyond objective lens system. So if my objective lens is doing a magnification of 100x, right? Then my intermediate, if my objective lens is doing a magnification of 100x, I means ideally one lens I do not want to create a magnification more than 1 lakh or 2 lakh or very high magnification. So that is why I have created the projector lens system, and the job of this projector lens system is to magnify. How the magnification happens? This 100x, let's say. Okay, so if I am talking about this 100x, and then let's say my intermediate lens is giving me 20x magnification, then similarly I will be keeping one projector lens also one projector lens I will keep it at 100x. Okay, so when I talk about all these things, and if so when I keep this lens system, objective lens system or the projector lens system, then the final image, let's say this will be my final image. Okay, so when I get my final image at the detector, this will be having how much? 2 lakh magnification, because here 100 into 20 into 100. So this is how I am able to achieve nearly 2 lakh magnification here I have told, but with the addition of other lenses also sometimes we are able to achieve millionth magnification, that means 20 lakh magnification also we are able to see. So this is how since the resolution is also high, it is not important that since the resolution is high we will be using one lens, so because that will create lots of aberrations, and that is why we are using different sets of lenses which will take us to extremely high magnifications. Okay, and the instrument, if I am talking about, this is the simplified schematic diagram of the instrument. Electron lens will be there, electron source will be there, and then condenser lens will be there, objective lens, and intermediate lens, which I was talking about. The job of this intermediate lens and the intermediate lens is to magnify it, and the projector lens also, the job of projector lens is also to project the entire image into the screen, into the viewing screen. So this is a typical schematic diagram of a transmission electron microscope. Okay, and here if you can see each image which is getting formed by its previous lenses, they act as an object for its further lenses. The previous, if I am talking about, this is my previous. If I am going up the column, then that is previous, and this is further. If I am going down the column, then this is further. And here this is an schematics of that we use here. This is a optic axis and gun crossover, you can see. So condenser lens, this is the C1 crossover, then here the first gun crossover, then after that once the beam gets through the condenser, then the C1 crossover, then you can see when the under focused beam is there, and also with the use of C1 by manipulating the strength. So C1, C2 is condenser lens 1 and condenser lens 2. So by manipulating the strength of this condenser lenses, what do I mean by strength of this condenser lens? That means I am increasing or decreasing the current that are flowing through the wires which are creating this electromagnetic lens. So when I do that, then I will be able to get, if I want, then I will be able to get an under focused beam. If I want, I'll be able to get a parallel beam. Most of the time we are using this parallel beam, because this parallel beam, when we are using, we use it for diffraction. Okay, so to obtain diffraction pattern we use the parallel beam. And also in some cases you might be seeing C2, yeah, so by using this configuration, if we want, we use sometimes under focused and sometimes we use this parallel beam. Then also it is not necessary that we always use the parallel beam. Why? Because if we want to see a particular structure, let's say I have a matrix, and in that matrix I have some second phase associated with it. If I want to get information only from that second phase, I cannot allow all the beams to fall on that, because in that case, if I, let's say I take a diffraction pattern here, then the diffraction pattern will be consisting information from the matrix as well as the second phase particle. In that case, what I will do, I want to focus my beam onto this particular spot. Then if I want to do that, that is what that means I am converging my beam. So when I am converging my beam, so I can do that by increasing the C2 current, so that the convergence I will both in C1 as well as C2, so that my the convergence of this electron beam will take place. And remember, here I have given one C3 lens. C3 means condenser 3 lens. It is not a condenser 3 lens, rather it is a combination of, so this lens is called as CO lens. CO means condenser objective lens. So this objective lens has been divided into two types. In this case, in this scenario, the objective lens has been split into two types. One will be of which will be in condenser lens system, and another one will be in the objective lens system. So in the C3 lens, when I am putting, you remember, you see it here, that C2, that means my condenser lens, I'm not using my condenser lens. What it will do if I'm not using my condenser lens? See here, if I'm using my condenser lens in this case, okay, my DI means here, this is my DI and this is my DO. Okay, so this will be my DI, this will be my DO. But when I am putting this lens, means I am not using this condenser lens, rather I am using a CO lens, condenser objective lens, the upper part of which is considered as C3 lens and the lower part of which is considered as objective lens. When I am using this kind of CO system, then what is the case? My DI is getting low. And if I am talking about, so DO means nothing, the object distance, that means U, in which is a familiar term to you, and my DI is nothing but the V, that means image distance. If you remember, we have told that in electron microscope the D magnification will be always high. So in this case, U by V, D magnification is considered as U by V. And what will happen, this D magnification, what do I mean by D magnification? If my sample is, that means my sample will, in my sample the area will be scanned this much, but in my image I will get a very higher image, that means a broader image I will get, right? So that is what I mean by D magnification. Okay, and the D magnification, if I am talking in the second case, my D magnification D naught by DI, or you can say U by V in the second case, will be very, very high, right? So very, very high means, if so what do I mean by physically demagnification? If my this crossover is in the order of 50 micron, do I need this probe size to be fall on my sample? No, I do not need that. In my sample, what is the order that I need? I need my probe size to be 1 nanometer. This is the physical significance of demagnification. My probe size here is 50 micron. My probe size here, when it is hitting my sample, it is 1 nanometer. That means from 50 micron to 1 nanometer reduction in my electron beam size, that is what known as demagnification. And in this case, when I am converging beam using C3 lenses, that means condenser objective system, my demagnification will be very, very high, and I will get a very fine probe which will give me better resolution. Okay, and using this thing we are analyzing this technique. One will be XCDS, yields, CBD. This CBD is known as convergent beam electron diffraction. Okay, and HADF, this HADF, this is called as high angle annular dark field. This is a technique in TM, high angle annular dark field. Okay, this is known as HADF. So this is the different types of beams that we operate in our electron system. And then comes depth of focus and depth of field. So these are the terminology which we have. So these are the terminology which we have seen earlier: the depth of focus and the depth of field. So depth of field corresponds to always the object, how much we can move in our object, how much we can move, and the depth of focus, it is always refers to the image. Okay, and if we take the geometric calculation using these two images which have been magnified in here, then if I am talking in terms of alpha IM here, if I am talking the image side, then the alpha IM, if since this this alpha angle will be very small. Why this will be very small? Because if we are increasing our alpha, then in that case the aberration will also increase, which will not give us a perfect image. So if I am talking about alpha Im, then in that case it will be closely to tan alpha Im I can write, and if I take the geometry here, then the tan alpha Im will be dim by 2 divided by dim by 2. If you do a geometry, this thing we have calculated earlier when we are studying about the depth of focus in scanning electron microscopy. So similarly also we can write beta object here, we can see, because our object will be here, our image will be formed here. Okay, so beta object will be close to since it is a small angle, so we can write tan object dob by 2 divided by dob by 2. Okay, so this is how so these are the two angles by calculating the distance from screen to our material, and where the gun crossover is happening, we can calculate the alpha, means the angle, the convergence angle. This is these are known as the convergence angle. We can calculate, and by calculating those things we can calculate the angular magnification. So the angular magnification, if I am writing, so angular magnification means how much magnification happening in terms of in this direction, that means in horizontal direction. If I am giving that value ma, so that is given by alpha Im by beta objective, which we have derived it here. Okay, so this is geometrical derivation we can do. And then transverse magnification, that means what is the magnification that is occurring in terms of this direction, that means the horizontal direction, vertical direction. If I am talking about transverse magnification, then that is given by dim by d object. Here if you can see, dim is nothing but the distance from how much this thing is, and d object is nothing but the distance from this one. Okay, so dim by d object, how much magnification, let's say this is our object, okay, and how much magnified image we are getting, that will give us our transverse magnification. And the depth of focus, if I am talking about depth of focus, the focus is related to image, so depth of focus is related to image, that will be given by d objective by beta objective into this square. And if I am talking about depth of field, then field is related to always object. Okay, here image, field, this is dob by beta ob. These are some of the formulas that you can derive by this geometry. If you take this geometry, then you will be able to derive. Okay, and yes, finally we are not able to another formula I just want to write here. So the depth of focus is related to the depth of field. If I am talking depth of focus is related to d image is d object m square by alpha. So this is the formula you can remember. The depth of focus is related to the depth of field by this magnification, and this alpha is the convergence angle, semi-convergence angle. Okay, and but what is then comes another terminology, that is resolution. Resolution is nothing but the minimum resolvable distance, as we know, as we have been studying throughout this chapter as the course. And this resolution is given by Rayleigh's criterion, right? So what is the Rayleigh's criterion? Anyone can say? So here this is there are three different cases which we have taken, that if these are two different point sources, okay, P1 and P2, so here they are completely resolvable, here they are not resolvable at all, and here they are partially resolvable. Okay, and partially I mean this is just resolvable. So just resolvable means if you bring them together furthermore, then you will not be able to resolve the two different sources. If you take them away, then you might be able to resolve. So this is what Rayleigh's criteria, and the Rayleigh's criteria is given by, so Rayleigh's criteria, what is that? So if I am talking about the distance, then d, if I am talking about, then this is 0.61 lambda divided by 0.61 lambda divided by mu sine beta. Okay, so here mu is the diffractive index, beta is the semi-convergence angle, lambda is the wavelength of the radiation. However, If we are talking about extremely low angle, then in that case this Rayleigh's criteria tells us that that means these 2 points will be fully resolved when the maximum from one, that means the maximum from this source is lying at the minimum of the other. Okay, and at that time they can be fully resolved if this intensity will be resolved, and this intensity will be 80% of the maximum this intensity. Okay, so that is what the Rayleigh criteria is. And finally he gave the formula that this should be the so this should be the diameter, this should be the diameter of this, no, not diameter, this should be the radius of this airy disk if you see it from this side, from the top. This is a side angle. If you see it from the top, then it will be appearing as two airy disk. Airy disk is, so this kind of thing will be there, and then okay, so these two top, when you see from the top view, so there will be two, you can see this kind of thing. And now this the radius of this airy disk, if it is 0.61 lambda by beta, then you will be able to resolve this distance between them, otherwise you will not be able to resolve the distance. Okay, and so this is the theoretical limitation of the theoretical limitation on the resolution. Okay, so if you put this thing into your expression, then you will be able to see that the resolution is coming well below angstrom level. Then if the resolution is coming well below angstrom level, then what is the need of other system? That means we are going to put our sample in the transmission electron microscope and we will be able to see the distance between the atoms. However, that is not the case. Why? Because of the presence of the aberration. And one of the major aberrations which is present in the transmission electron microscope lenses, that is the spherical aberration. What do we mean by spherical aberration? The more these electrons will be going away from the optic axis. If I am talking, this is my optic axis, the more they are going away from the optic axis, the less the more focus they will be close to this lens. So that means the lens which is going this beam, it is focused here, and this beam somewhat focused here. Okay, and due to this kind of focusing, there will be plane of least confusion which will be getting formed. And in the image plane, if you are putting your detector, you will get a disk diameter of 2 CS beta q. So here beta is nothing but the aperture angle, CS is known as the coefficient of spherical aberration. Okay, so and here in the disk diameter, the plane of least confusion is 0.5 CS beta q. Okay, so the more and the more beta, that means the convergence semi-convergence angle will be there, it is the aberration will also be increased. So that is why we don't want our beta to be too much high in terms of electron microscope. Okay, and how to calculate? So when this spherical aberration now comes into picture, then Hawke's treatment has been taken, and then finally the radius of this the radius of our resolution limit has been defined as like this from Hawke's treatment. And how this entire expression varies with if I want to say, this entire expression varies with beta. Beta means the semi-convergence angle. We can put our all the formulas here. Beta plus, let's say, 0.5 CS beta q, this is 2 and whole to the power half. Now beta is there, so when we now now this beta is there, and if we want to calculate that what will be the optimum beta angle for our material, so what we can do, we can calculate the derivative and put the beta and put it to 0, so that we will get an optimum angle, optimum disk, optimum airy disk, optimum radius of the airy disk for which our aberration will be as minimum as possible. So that expression I am just writing it here. So that beta optimum, when you put this thing to 0, the beta optimum you will be getting 0.77 lambda to the power 1 by 4 cs to the power minus 1 by 4. And using this optimum semi convergence angle, if you calculate the minimum value of the airy disk or the minimum resolvable distance, then you will be getting 0.91 cs 1 by 4 and lambda 3 by 4. And this expression, if you remember, one of our previous practice question, when the spherical aberration comes into the picture, how the R minimum gets affected, in one of our practice questions we have derived. And the reason for that is, how we have derived that thing, we have first put this in the function of beta, and then we equated that, we took the derivative and we calculated the beta optimum, that means the optimum semi convergence angle, which will give us the minimum the radius or the minimum diameter of our airy disk, which is the ultimate terminology for calculation of the resolution of our system. So, and finally we will be getting this expression, we will be coming out with this expression. And now so far we have already always for any electron optical system, we have told that there would be a terminology called aperture. So what is that aperture that we are talking about? That aperture is associated with all the lens system, whether it's a condenser lens system, whether it's an objective lens system. But what is that aperture, and what is the role of that aperture? Is to control the divergence or the convergence of electron path. Okay, and why we need to control the this aperture, the role to control this electrons? Because if we are not controlling those electrons, then the lens aberration will play an effect in imaging of our material. Then the amount of current beam, when we do not need high amount of current hitting our specimen, those things will also be coming into picture, and they will affect our materials imaging, materials information that we are going to extract from the different diffraction pattern. Okay, and yeah, so how we are what is the here, if you see here, there are different types of aperture which you can see, and these are the different so this is a slit along which you can see the small here your different aperture. So this is a size of the aperture, that means the if you are using this aperture, that means you are allowing more current or more beam to go and hit your specimen. Here you can see the specimen, this is after the this is the objective, if I am talking about. So this is the objective lens system. Okay, and after objective, let's say this is the intermediate lens system. So after specimen, after the electron beam interacts with the material, you can see I do not want high angle electron beam, I do not want to collect high angle electron beam on my detector. So I will limit the this aperture, or also sometimes it is called as diaphragm. Okay, so I'll put this aperture so that all the beams which are coming in at a very high angle, I do not want to collect those things. So I will collect a certain amount of beams which are necessary for my material. Okay, and the role of this aperture is to, like I said, control the collection angles. When you control the collection angle, it will also increase your resolution of the image, and definitely it will give you an image contrast based on the position of the aperture. We will see in the subsequent classes how the image contrast we can manipulate, how we can get bright field image, how we can get dark field image, how we can get, there is a terminology called ADF, annular dark field image, how we are going to get those images. Okay, and how the angular resolution of the diffraction pattern also is dependent on aperture. So that is also another function. And collection angle of yields, we'll see how aperture controls the yields, that means electron energy loss spectroscopy. Okay, and since we are talking about different instrumentation, pumps and holders also play a certain role in the imaging techniques of transmission electron microscopy. In the TM column, I told that the vacuum that we have to maintain is 10 to the power minus 5 Pascal. To maintain this kind of vacuum, we need different types of pump. So mechanical pump, diffusion pump, or so these are the different types of pump. Ion pump, if you can see. So we implement all those pumps into our a transmission electron microscope, so that this column, TEM column, will be maintained at a high vacuum. And into this TEM column, this specimen, since I told that the sample shape cannot be random, it has to be, there is a limitation to which we can put our sample. So there are different types of holders are available, those are called TEM sample holder. And if you can see, there is, after O-ring, this entire portion, this will be in the TEM column, that means inserted into here. And that this portion beyond all this, this section of this sample will be in the vacuum during your operation. And here you can see, this is a heating, this is a rotation holder, which that means you put your sample here in this white area. You can see, you put your sample here and then you can rotate. So this is a rotation. This is a heating holder, that means this holder is capable of heating your sample. If you are heating your sample and then want to analyze what is the in situ experiments or the in situ phenomena is doing to your material, then you can do. This is a cooling sample holder, this is a double tilt holder, and this is a single tilt holder. Okay, so double tilt and single tilt, I mean, okay, so this is one type of tilt and this is another type of tilt. So it can rotate along x-axis as well as y-axis. If we are considering that this is x, then this is y. Okay, so this is a single tilt and double tilt holder. Heating, cooling is important for us to understand the phase transformation or the in situ phenomena that is taking place in our material. Okay, and yeah, this is also a multi, so this is what, a multi specimen holder, and this is a single specimen holder with different also this is a single tilt holder with two different sample. So these are different types of holders that we use for our for viewing our sample into the specimen chamber. Okay, and this is the diffraction pattern and images that this is the basic phenomena behind how we are getting diffraction pattern and how we are getting final image. So the most important parameters here is in the column. If we remove our objective aperture from here, if we remove our objective aperture, then finally we will be getting, in our screen we will be getting the diffraction pattern. If we are inserting our objective aperture in the back focal plane of the objective lens and we are removing the SAD aperture, SAD aperture, okay, SAD aperture means selected area diffraction. Okay, so SAD is selected area diffraction. So that is why the diffraction pattern we generally obtain from TM is known as SAD, selected area electron diffraction. Okay, so if we are removing this SAD pattern here in the second case, okay, then we will be getting the final image. So these are the different instrumentation we have to remember when we are going to put our sample in the electron column. Okay, so these are the concepts behind the operation of transmission electron microscope. Now we will be seeing some of the conceptual, we will be going through some of the conceptual questions. Okay, so this is our first question. Which of the following statements about transmission electron microscopy is correct? Okay, TEM uses electrons to illuminate a sample producing a three-dimensional image. This is the question for option A. TEM can achieve a higher magnification than scanning electron microscopy. This is option B. And then TEM is primarily used for imaging the surface morphology of the samples. This is option C. And TEM samples are typically thinner than those used in scanning electron microscopy. Okay, which one will be the correct answer? Can anyone say? People are there? Yes. Okay, anyone? So okay,
TM uses electrons to illuminate a sample producing three-dimensional image. This is a wrong statement because TM does not produce a three-dimensional image. It produces a two-dimensional image. Okay, so 2D image it will produce. TM can achieve a higher magnification than scanning electron microscopy. Yes, it is the correct statement. TM can achieve a higher magnification, and TM is primarily used for imaging the surface morphology of the sample. No, it can collect information from beneath the surface morphology of the samples. Then TM samples are typically thinner than those used in the scanning electron microscopy. Yes, this is also a correct answer. Okay, so here maybe this is R correct. Okay, so these two are the correct option. These two are not correct options. Okay, and yeah, so here is the explanation also. In transmission electron microscopy, samples are typically thinner to the region that though the penetration depth of electron is 100 nanometer, for TM microscopy we keep our sample the thickness of the sample is close to somewhat 5 to 20 nanometer. So this is the typically we make our sample in such a way that first we let's say we cut a sample, and then the thickness, so this thickness will be, we keep this thickness is 100 nanometer, right? So this thickness we keep it as 100 nanometer. Then there is a process called dimpling. So in that dimpling, what we do, we keep this area, okay, this will be 100 nanometer, and this distance we keep it close to 30 nanometer, right? So once we keep close to 30 to 50 nanometer, so then there is another process called jet polishing for metals or PEEPs, that, and that is for ceramic and other hard materials. Through that, what we do, we almost, so this, there will be a hole, small hole will be created. However, around this hole, if you talk about, so around this hole the thickness will be close to 5 to 20 nanometers. So that is how, so this is a dimpling. Before dimpling, so this is polishing. We do the polishing first, bring it to 100 nanometer, then we do the dimpling, and after that either we do PEEPs or jet polishing. Okay, and finally this specimen is taken, and by we do the cleaning, ion cleaning, and then finally we put it in the sample holder. However, this distance is still 100 nanometer, so we don't touch the edges, rather this is how we prepare the sample. Okay, so the second question is, which of the following statement is true? Why TM images have much higher resolution than images from light microscope? Statement 1 is TM is much greater than size than greater in size than light microscope. Electrons traveling as waves have wavelength much shorter than visible light. TM can achieve greater magnification. The fluorescent screen of TM can generate high resolution image. So which are the correct statement? Can any one of you tell? Anyone? Okay, we'll go through that. So statement 1 is TM is much greater in size than light microscope. No, this is not the case, because TMs may indeed be larger in the physical size, but due to the complex system that are associated with it, but to manipulate the electron beam, but that is not the case. For getting high resolution, electron traveling as waves have wavelength much shorter than the light. Yes, this is the correct statement. TM can achieve greater magnification. Yes, that is also correct, that it can achieve greater magnification. And fluorescent screen of TM can generate high resolution image. Screen does not have any correlation with the resolution of the image, because screen will only show us after the interaction of this electron beam with our material. It will only produce the it will only shows the image that we are going to see, but it only converts the electron signal that is coming after the interaction, and finally it converts into visible image. Okay, so that is why the role of screen is it doesn't influence the resolution of the sample. So this is a wrong answer. So this is also wrong answer. That means statement 2 and 3. So 1, 2, 2 and 3, B will be the correct answer. and the explanation also, since this explanation everything I have given it here, so you can read it. Which of the following, question 3 asks, which of the following is the correct pathway of electrons in the TEM? Out of the 4, which one is the correct pathway? Can anyone say? From the electron column that I have drawn, which one is the correct pathway? From the TEM column. Anode electromagnetic lens system sample fluorescent screen, anode electromagnetic system sample electromagnetic lens fluorescent screen, cathode, and yes, these two, out of which the correct option will be, I'll just check if anyone has written anything. Okay, no one has written. Which one will be the correct answer? The correct answer will be C. Sorry, is anyone speaking? Why C? Because cathode means the electron gun that is coming through the cathode. Then electromagnetic lens system means I am talking about condenser lens system here, and condenser lens system, then sample, after then electromagnetic sample itself stays in objective lens system, then electromagnetic lens system, then I am talking about intermediate lens system for further magnification, right? So, and after that fluorescent screen, right, where I see my image. So this is the correct answer, cathode electromagnetic lens system sample. Remember, this D also you can get confused, that after sample fluorescent screen. No, after sample there is a, if you put a fluorescent screen, there will be no further magnification. You are not going to achieve millions of magnification in that case. Okay, so then there will be no further magnification. That is why C is the correct answer. Here I have given the explanation, what is the role of each and everything: cathode, lens system, sample, lens system, fluorescent screen. You can go through them. Then the fourth question is, which of the following is an advantage of TEM over ACM? Higher resolution, faster imaging speed, higher depth of field, lower resolution. Can anyone answer?
Yes, sir. Higher resolution.
Yes, that is the correct answer. Which of the this is, since TEM is having resolution, it is capable of resolving between atoms, so that is why higher resolution. Faster imaging speed and depth of field, because electron microscope, since both are having electron microscope, so depth of field will be similar. Lower resolution TEM doesn't have, rather higher resolution. This is the, and the faster imaging speed depends on the type of system that we want to view. Okay, and then question number 5, this is a numerical question. What is the wavelength of the electron beam accelerated by a voltage of 100 kilo electron volt without considering relativistic effect? So relativistic effect means what will be, how the wavelength is associated with energy. The wavelength will be associated with energy in electron volt by formula called 1.22 divided by e to the power half. If we are considering the relativistic effect, then in that case the formula will be changed. But if we are not considering the relativistic effect, and remember here lambda will be in nanometer and E will be in electron volt. Okay, so that means you have to put this formula 1.22 divided by 100 kilo. Kilo means 110 to the power 3 into electron volt to the power half. I don't know how much this formula. Can anyone calculate and tell me? How much the value is coming?
Option C.
Okay, that means this value is 0.0039 nanometer. Yes. Okay, so this is the value that is coming, and yeah, you can see at so this is 0.39 nanometer, means it is close to so it is equal to 3.9 picometer, right, and close to 4 picometer. Yes, this is the wavelength of electron when you are accelerating the electron at 100 keV. electron volt. Okay, so this is what we generally get it. So this is why I told that the wavelength of the electron is in the order of picometer. Okay, so this is a question related. So this is a question when you are operating in the TEM instrument. So before loading the sample, the following software has to be turned on, except electron gun tilt shift, TEM imaging and analysis, microscope user interface, and digital micrograph. Can anyone answer this question? If anyone has anyone worked with transmission electron microscope, has any experience? Okay, so I'll tell. So electron gun tilt shift, so all these this one, and microscope user interface and digital micrograph, so these all will be opened before we load the sample, because after loading the sample we use these parameters or these conditions, so that we align the sample and then we create the vacuum. Then we generally the from let's say 0 to 200 kV we want to means ideally the potential that we that the gun is the potential that is present between the gun and our sample the ground is 0. So from 0 we go to 200 kV by step we go, and for that we need the microscope user interface. Once we go to 200 kV, then we and that user we the digital micrograph also, we use the digital micrograph, and then once we go to 200 kV we do all this electron gun tilt and shift, so that the incident beam and our sample will be perfectly aligned. There will be no astigmatism, there will be no shifting of our electrons, no wobbling, and or no other effects are also which are present, which will be associated with the beam and specimen interaction. We minimize those things, and then finally we prepare our sample. And here you can, even if you don't know this one, here the TM imaging and analysis, always remember analysis is carried always after, not before. Okay, so that is why the option B will be the correct answer. So the following statement is true or false. Ultraviolet light is applied to the sample to warm the sample. True, false, none of these. Can anyone answer? Whether UV rays are used to heat the sample? Anyone? Okay, this is a false answer. Why? Because UV rays are not used to heat up a sample. UV is generally used for different other purposes. One of the reason is fluorescence microscopy. Okay, and this also sometimes used for sterilization, and this also sometimes used for curing a sample. Okay, and also to if we have to initiate certain type of chemical reaction, so we use this thing for UV rays. It is not used to heat up the sample. Generally to heat up the sample we are using infrared. For heating we use if we are using heating thing, then we are using infrared. Okay, yeah, here I have written. Okay, now comes question number 8. All the following are true for both transmission electron microscope and scanning electron microscope, except which are not true. That means it is asking illuminating source is an electron beam. Microscope is focused using electromagnetic lens and can be used to view specimens smaller than 0.2. The specimen must be sectioned prior to viewing. So which one will be which one are correct, which statements are correct? It is asking which statement is incorrect. Can anyone answer?
Yes, sir.
Only 3. We'll see. The illuminating source is an electron beam. Yes,
Only 3.
correct. The microscope is focused using electromagnetic lens and can be used to view specimen. Yes. The specimen must be sectioned prior to viewing. No, prior to viewing there are polishing, dimpling, and then jet polishing. Other peeps is also involved. Then finally we do the cleaning also just before viewing. So this is not the correct. This is the wrong thing. And since it is asking which one is the incorrect thing, so option A is correct. Okay. Then question number 9, which of the following statement is or are true? Dark field image is formed by. Okay, we have not gone through bright field and dark field yet, but if you can remember the dark field and bright field phenomena from the light optical microscope, then you can answer this question. Blocking the transmitted beam and allowing the diffracted beam to pass through. Blocking the diffracted beam and allowing only the transmitted beam to pass through. Tilting the incident beam such that the diffracted beam passed through the center and blocking the transmitted beam. Which one is the correct answer? Dark field. Dark field means the background will be dark and the sample on top of the background it will be white. So this is what dark field. Bright field means background will be bright, sample will be dark. Okay, so blocking the transmitted beam and allowing the diffracted beam to pass through. That means if my sample is this and it is going like this, and in the viewing screen if I am not allowing this one, right, then in my viewing screen my only diffracted beam will be coming, and in that case what will happen? The background will be dark, right? So the background will be dark and my sample, let's say this is my sample, and this will be white. This all section will be dark because I am allowing the diffracted beam to come. This will be dark and this will be, my sample will be bright. So this is a dark field. That means statement 1 is correct. We will see the bright field and dark field, how they are getting formed, how the role of aperture influences dark field and bright field imaging in the next class. Blocking the diffracted beam and allowing only the transmitted beam to pass through. No, if the transmitted beam pass through, then it is bright field imaging. Tilting the incident beam such that the diffracted beam pass through the center and blocking the transmitted beam. That is also, this means if we do not want a parallel straight beam, then what we can do? We can simply, so here what we do, we put our aperture in such a way that we are only allowing the diffracted beam. Let's say I do not want to move my aperture. In that case what I will do? I will tilt the beam so that my diffracted beam can pass through. However, my transmitted beam will be deflected by or stopped by the aperture, right? So this is how I will also create another diffracted beam. So 2, 1 and 3, that means option B is the correct answer. Depth of focus in electron microscopy is very high. It is true or false? Can anyone answer? We have gone through this in the theory of transmission electron microscope.
True, sir.
Okay, yeah, this is a true, and the depth of focus is in the order of kilometer. So that is why below the electron, the specimen chamber, we can put our screen, as well as we can put different systems for chemical analysis like energy filters and all those filters we can put for analytical technique. Okay, is it all? Okay, I think this is the condenser lens controls the size and intensity of the electron beam in TEM. This is true or false option. We have gone through it in our lecture. Can anyone answer? condenser lens controls the size and intensity of the electron beam in transmission electron microscope. So when I'm talking about condenser lens, that means it is a condenser lens system, right? So in the system,
True, sir.
yes, it is also true, right? Because finally the gun crossover, the d naught value that we are getting from the topmost portion of the electron gun, that electron column, the d naught, that is the crossover. So after this d naught, this is called gone crossover. So after this gone crossover, condenser 1, condenser 2 will be there. So after that condenser 1, condenser 2, this is the so there will be one crossover will be there. This is C1 crossover, right? And then this will be C2 crossover. So they ultimately define how what will be the size and intensity of the electron beam. If any aperture is there, then they will block the unwanted beam, that means the most diverged beam, and likely they will control the intensity and the size of the probe. And I think this is the last question. To control the beam current and convergence beam hitting the specimen, dash is used, fill in the blanks. Okay, scan coil, sample holders, aperture, detector.
Can calls.
To control the beam current, not only the convergence of beam hitting the specimen, scan coils does not control the beam current. Means how much beams will be
Apertures.
apertures, yes. So not only controls the convergence but also the beam current, how much beam will be passed through any of the, whether it is an objective since hitting the specimen, that means before the objective lens. So before the objective lens, it is about the condenser lens system, and how much current will be coming, whether so all the currents are coming which are getting generated from the gone crossover, whether all the current should be hitting the sample, or some of the, we do not want that high intensity or that high current to hit our sample. If our sample is prone to beam damage, then in that case we use the aperture, we use the smallest aperture, so that not much damage can happen to our sample. Okay, so I think that is the end of our session.